So now is starting the transmission on YouTube. There is always a short delay. So good afternoon, good morning, good evening, everybody. So welcome to the launch of the 2021 season of IEEE Circuits and Systems Society Rio Grande do Sul talks. So these talks are generated from Porto Alegre. So we have the honor today to have as the first talk of the year, Professor Subhasish Mitra from Stanford University. But before doing a short presentation of him, I will just do some few announcements. So next week, we have also another very interesting talk in this series of CASS Talks 2021 that is also done together with the graduate program on microelectronics and the Informatics Institute of the Federal University of Rio Grande do Sul. So next week is Hi Helen Lee from Duke University talking about efficient deep learning at scale. Then we have already here the flyer for the next talk of the month that is with Professor Rajesh Gupta from UC San Diego, and he's going to talk about programming human spaces. Also, if you want to see some of the talks of last year, so we have a large set of talks that are available in this YouTube channel. So all the talks of 2020 are available there. Also, we have a set of industrial talks, and I don't put here in this window, but we have also the all talks related to our last CASS workshop that was done in October. So very interesting talks also, and other talks also. So we have a large set of talks to see there. You have also in the last edition of IEEE CASS magazine, fourth quarter of 2020, also a report with 10 pages about the CASS Talks 2020. So you have a nice set of talks to take a look. So just to remind you that in a few weeks we have the LASCAS 2021, so virtual edition this year, together with Iberchip and Prime LA. So with a very nice program, and the registration this year, exceptionally for CASS member, is a free registration. So, but there is a deadline for that. So if you want to do this, please do as soon as possible. Then also in end of April, we have our traditional South Microelectronics School, the 23rd edition, and the 36th edition of South Symposium Microelectronics. So soon you are going to see some more announcements. And November 2021, we have the 17th edition of Ceresa, that is the school dedicated to circuits tolerant to radiation effects. So I hope that this edition will be a face-to-face one with everybody already vaccinated. So also in July, I don't have the slides here, we are going to have the first edition of the seasonal school on monolithic 3D. So we are starting to prepare the program, and editions the years after should be in France, Singapore, China. So why not in USA, Mitra? So then I'd like here to give some few words about Subhasish. So first of all, thank you very much for accepting our invitation. So Subhasish Mitra is a professor of electrical engineering and computer science departments at the Stanford University. He directs the Stanford Robust System Group, leads the computation focus area of the Stanford System X Alliance, and is a member of the Wood-Tsai Neuroscience Institute. Professor Mitra also holds the Carnot Chair of Excellence in Nanosystem at CASS in France. So his research ranges across robust computing, nanosystem, electronic design automation, and neuroscience. Results from his research group have influenced almost every contemporary electronic system and have inspired significant government and research initiatives in multiple countries. So Professor Mitra also has consulted for major technology companies, including Cisco, Google, Intel, Samsung, and Xilinx. So Professor Mitra's honors included the Newton Technical Impact Award in EDA, Test of Time honored by ACM CDA and the IEEE Council in EDA, the Semiconductor Research Corporation's Technical Excellence Award, the Intel Achievements Award, that is the Intel highest honor award, and the US Presidential Early Career Award. And he has published award-winning papers at major venues, and he is an ACM Fellow and IEEE Fellow. So this is just a very reduced words about the large CV that in the achievements that Professor Mitra has already achieved. So it's another honor for us to start this 2021 series of CASS Talk with a presentation by Professor Mitra. As you can see by the title, it would be a very inspiring one. So thank you very much, Professor.
Thank you very much. Thank you, Ricardo.
And the floor is with you to start your presentation.
Thank you, Ricardo. And it's truly an honor that you invited me to kick off the 2021 talks. So thank you. I highly appreciate that. And I have to say that I have visited Brazil a couple times, and Sergio is here, and Ricardo, you're here. You folks have been like absolutely awesome hosts. And I was at SBCCI in Aracaju a few years back. And thank you very much for having me there. I have enjoyed my trips to Brazil every time I have been there. Okay, and so I'm looking forward to my next trip to Brazil.
Yeah.
So, hi everybody. Again, good morning, good afternoon, good evening, depending on what part of the world you're in. So I will be talking about 21st century nanosystems for abundant data computing, especially our Next 1000X project. But before I start my presentation, I want to thank my students, my sponsors, and my collaborators, without whom this work wouldn't have been possible. There is an explosive growth in our dependency on computing systems. The whole world expects these systems to grab massive amounts of data, the so-called abundant data, and compute on that data from the edge to the cloud to solve global grand challenges. Now, right at this point in time, when the world is expecting exceptional capabilities from computing systems, massive degrees of performance, right at this point in time, we are hitting a red brick wall. And this point has been articulated very well in this article from the US National Academy of Sciences, which I strongly encourage you to read. This is called The Future of Computing Performance, Game Over or Next Level. Now, since we are talking about performance, let's look at what I mean by performance in this talk. By performance, I mean energy times execution time. The reason is the following. There are many ways to improve energy at the cost of execution time. For example, by reducing voltage. There are many ways to improve execution time at the cost of energy. For example, by increasing voltage. But there are very few ways of improving energy and execution time simultaneously. So that's a metric for computing performance that we will use in this presentation. Now, since we are talking about performance, we have to think about applications. And the applications that we are going to focus on in this presentation are what I started off this presentation with, the so-called abundant data applications. Now, one feature of these abundant data applications that I already introduced in the beginning of this presentation is what is called the memory wall. So as you can see in this pie chart, if you look at either energy or execution time, you will see that a significant chunk of the energy or execution time is spent trying to access memory. This is called the memory wall. And this is irrespective of whether you have processors or whether you have hardware accelerators. And it's also irrespective of the particular compute model you're using. For example, you could use neural nets for machine learning, for example, or you could use, computing models for machine learning that are beyond neural nets. For example, the broad set of brain-inspired computing models. You see the same challenges, the challenges of compute plus memory, dense connectivity, and energy efficiency. Now, the memory wall is not the only wall we have to worry about. There are many other walls that we have to worry about simultaneously. We have already been living with what is called the power wall, with the slowdown of Dennard scaling for almost a decade now. And moving forward, we are going to hit what is called the miniaturization wall, which I'm showing with these Russian dolls on this slide. We are at around a 5 nanometer technology node today, and the question is how far we are going to go. Maybe perhaps 0.5 nanometer, we will see. So then the question is, how do we overcome all these walls, the memory wall, the power wall, and the miniaturization wall simultaneously, and still achieve massive improvements in computing performance? So how do we improve computing performance? Well, if I were a device person, I would say one way of improving computing performance is through better devices. Now, while there are many ideas of interesting devices in the literature, there are very few experimental demonstrations of these better devices. And even more importantly, a device is not the same thing as a system. So we have to think about more broadly. Now, wearing my hat of a designer, another way of improving computing performance is by playing design tricks. For example, we have already played the multi-core trick. Today we are playing the accelerator trick, which is I'm showing as an ASIC on this slide. And of course, while we play these design tricks, we also have to deal with power and thermal management and so on and so forth. We are already playing these tricks today. And even more importantly, as we play these tricks, we incur massive design complexity. And as a result, design bugs become very important. I know of so many design tricks, but very few of them are played in real life, simply because we may not be able to verify that these design tricks are actually going to work in a bug-free way through very thorough verification techniques. So the question is, if we want to improve computing performance by, let's say, 1,000 times, again, remember by performance, I mean energy times execution time. And if I want to improve that energy times execution time metric by 1,000 times, clearly I need new innovations, which would be a combination of new technologies or new devices and new design techniques. And this is what I call nanosystems. So to build nanosystems, first we have to think about nanotechnologies. So when I say nanotechnology, I just do not mean new devices. I also mean new ways of doing fabrication or even new sensors. Now, the trouble with nanotechnology is that it's very interesting that on one end of the spectrum, you're talking about things extremely small. For example, today, I'm going to talk about things at a 1 nanometer scale. And on the other end of the spectrum, you're going to talk about many devices on a chip. So now, if you're talking about many devices, many things on a chip that are extremely small, then you have to worry about imperfections, you have to worry about large-scale fabrication challenges, and you have to worry about variability among all these devices. Now, when you're successful in overcoming these challenges, it is extremely important that we enable new architectures that are not possible with existing nanotechnologies. So what we essentially talk about is, and this is key, we cannot just take existing architectures and we just replace existing devices with new devices on these existing architectures. To get major benefits, it's absolutely crucial that we enable new architectures using these new nanotechnologies that are extremely difficult or almost next to impossible using existing technologies. And when we create these new architectures, we enable new applications. For example, the abundant data applications that we are focusing on in this presentation. Now, how do we do that? If we think about architectures, what architectures do we use today? How is computing done today? In spite of massive progress over the past 60 years, computing the way it's done today is, fairly, fairly simple. I do not want to use the word simple in a derogatory way. So we have this kind of a two-dimensional plane of transistors. We have the compute chip over there and the memory chip over there. So we have this two-dimensional plane of transistors. Yes, we have some wires interconnects in the third dimension. That's a compute chip. And we have the memory chip sitting very far from the compute chip. And we have to go back and forth between the compute chip and the memory chip, causing the so-called memory wall. And as I already discussed, that with the miniaturization wall that's coming forward, the question would be, how can we move forward? Instead, moving forward, if we think about how computation should be done, it would be through the so-called next nanosystems, where we have layers of efficient logic. We have layers of dense memory interleaved with each other. We could think about layer of increased functionality, for example, sensors. But I really want to draw your attention to this very important point, which is these layers of efficient logic and these layers of dense memory interleaved with each other. They have to be connected with each other using ultra-dense three-dimensional connectivity. And that is the focus. That's how we achieve what is called computation immersed in memory. And that is the focus of this presentation of next nanosystems. Now, this structure is impossible with business as usual. So a few years back, a bunch of us, we got together to put this vision together, which is called Nano-Engineered Computing Systems Technology, or NEXT in short. And I strongly encourage you to read these publications that provide an overview of this NEXT approach. And NEXT also forms the basis for what kind of a metric for quantifying the advances in semiconductor technology we think about moving forward. Today we think about a 5 nanometer technology node, a 3 nanometer technology node, a 2 nanometer technology node, and so on. Moving forward, we might have to think about what is called this LNC metric. It's a density metric where L stands for logic density, M stands for memory density, and C stands for connectivity. This is a proceedings of the IEEE paper that I co-authored with a few of my colleagues in 2020, that is last year. I strongly encourage you to look into that. Now, next, the way I explained to you is a concept. Remember, we have multiple layers of computing logic, very efficient computing logic. We have multiple layers of dense memory interleaved with the computing logic, and we have ultra-dense 3D connectivity. Now, that's a concept. The question is, what technologies would you use to implement next? Now, one thing I have found over these years is that many of you are experts in semiconductor technologies. So when we have many experts in a room, we have many opinions of how to implement next. And one answer that everybody agrees on, if you get a bunch of these experts in a room, is the common answer that everybody would agree on is my technology. Now, since I have the honor to give this presentation today, let me tell you that how we are implementing next at Stanford right now. So to implement layers of efficient logic, we are mostly focusing on one-dimensional carbon nanotube transistors, and we are also looking at two-dimensional FETs as well. To implement dense memory, we are looking at two memory technologies, magnetic RAM and three-dimensional resistive RAM, because MRAM and 3D RRAM, they have complementary capabilities with respect to density, with respect to retention, with respect to endurance, and so on and so forth. But I want to highlight a few really important points over here. First of all, remember when I introduced the next concept, I talked about the importance of ultra-dense 3D connectivity. So for connecting these multiple layers of computing logic and memory, we do not use any through-silicon vias. Instead, we use ultra-dense, fine-grained vias through what we call monolithic three-dimensional integration. We will talk about that. That's the first really important point. The second point is, although we are using new technologies, for example, carbon nanotube FETs or resistive RAM and so on, this whole architecture is fully compatible with silicon technologies. And as I will show you later in this presentation, these approaches are being implemented in actual silicon foundries. So this is fully compatible with silicon technologies. And number three, when you think of three-dimensional integration, you naturally think about thermal issues, like how do you get the heat out from the upper layers. Now, in the first generation of our next architecture, the transistors and that are being used on the upper layers, those transistors are being used to access memories. And as a result, we are not running heavy-duty compute on the upper layers of this stack. The heavy-duty compute is running at the bottommost layer of the stack next to the heatsink. And as a result, thermal is not a challenge in the first generation of our next architecture. Now, moving forward, when two-dimensional miniaturization really stops, then we have to think about heavy-duty compute on the upper layers of this 3D architecture, and then thermal becomes extremely important. And this next concept is the basis for a major DARPA program in the US. This is called the DARPA 3D SoC program. This is a collaborative program between MIT, Stanford, Skywater Technology Foundry, and Nano-Integris. Professor Max Schulaker, my former PhD student from MIT, he is the PI, and he's collaborating with Professor Anantha Chandrakasan of MIT. From Stanford, the people that are involved, the faculty that are involved include Professor Simon Wong, Professor Philip Wong, Professor Boris Morman, and myself. Skywater Technology Foundry is a silicon foundry that's implementing all these technologies, the carbon nanotube transistors, the resistive RAM, and the monolithic 3D integration. And Nano-Integris is a carbon nanotube supplier. So now what I'm going to do for the next part of this presentation is I will be focusing on the individual technologies, the carbon nanotube transistors, the resistive RAM, and the monolithic 3D. So carbon nanotubes are nanocylinders of graphene with fantastic electrical properties. When you grow carbon nanotubes on a substrate, or when you transfer carbon nanotubes from one substrate to another substrate, and then print these source, gate, and drain contacts, what you create is a carbon nanotube field effect transistor. Typical carbon nanotubes that we grow in our lab, they have a diameter of somewhere between 1.2 to 1.5 nanometer, for example. On this image, over here where my mouse is, you can see this image of carbon nanotubes. So why are we looking at carbon nanotube transistors? Because a study that we did jointly at Stanford with IMEC and TSMC shows that when you actually replace silicon transistors with carbon nanotube transistors and obviously optimize the design, remember it is at a full design level. This is not at a transistor level or a NAND gate level. And when you replace silicon transistors with carbon nanotube transistors and then optimize the design, you get very significant benefits in energy delay product at a full design level. Now, in the past, in spite of significant promise of these carbon nanotube technologies, people could not actually build actual working systems with carbon nanotubes. And that's because of significant imperfections that are inherent with these carbon nanotube technologies that had to do with the so-called mispositioned carbon nanotubes and metallic carbon nanotubes. Now, those have been past obstacles. So using an approach which is called an imperfection immune approach, where we kind of combine new fabrication techniques with new design techniques, we have been able to overcome these obstacles. And as a result, now working systems built out of carbon nanotubes are actually possible. A few years back, my group at Stanford, we demonstrated the first carbon nanotube computer. It was a very small microprocessor with only 178 carbon nanotube FETs. It was a PMOS logic that was implementing a single instruction, but it was Turing complete. So you could actually run software on this microprocessor. But I'm very proud to tell you that in end of 2019, our colleagues at MIT, led by Professor Max Schulacher, they actually demonstrated a full RISC-V microprocessor. This is a collaborative work within MIT and Analog Devices, a full RISC-V microprocessor with full CMOS, with carbon nanotube FETs. And what I often highlight is that while the carbon nanotube processors grow, students also grow. So this is Max Schulacher, who was the first author of the first carbon nanotube computer paper back in 2013 that came out in Nature, and now he's Professor Schulacher, who demonstrated this RISC-V carbon nanotube processor. Worldwide, there have been major innovations in carbon nanotubes, both from the aspects of complexity. So, I talked about, starting from the first carbon nanotube computer, and now you have a full RISC-V microprocessor built completely out of carbon nanotubes, to scalability, where you have very scaled carbon nanotubes. Very recently, our colleagues at Peking University demonstrated very high degrees of carbon nanotube density, for example, with really great alignment. And Professor Schulacher's group from MIT, again in 2020, last year, they demonstrated establishment of a carbon nanotube transistor technology in Silicon Foundry, the Skywater Technology Foundry. And so far as performance is concerned, there have been significant improvements that have happened. And I would like to highlight this work that came out in IEDM 2020 in December last year from TSMC. So major carbon nanotube FET innovations are happening worldwide. So that's carbon nanotubes. But when I introduced our next architecture, remember I talked about that we have to think about efficient logic, we have to think about dense memory, and we have to think about ultra-dense connectivity. So let's focus on dense memory. So we are focusing on resistive RAM as dense memory to have very large amounts of on-chip memory, much larger than what you can have with existing SRAM. So some of the benefits of resistive RAM include non-volatile system operation. For the first time, we have been able to demonstrate multiple bits per resistive RAM cell at a full array level. There is this notion of 1T NR structure of resistive RAM for high density, which I will talk about. And by using new resilience techniques, we can actually achieve 10 years of continuous edge AI using resistive RAM. So let's look at resistive RAM for the next part of this presentation. So as I told you that our group has been able to demonstrate for the first time multiple bits per cell resistive RAM at not only at a full array level, but also to demonstrate actual computing systems. This was demonstrated at ISSCC 2019, where we had resistive RAM storing multiple bits per cell. So while in the past, people demonstrated multiple bits per cell of storage with resistive RAM, maybe at a single cell level or at a few handpicked cell level, we were the first ones to demonstrate 3 bits per cell resistive RAM at full array level, in this IEEE TED paper in 2019. And at ISSCC 2019, as I was referring to, we demonstrated a complete computing system where the on-chip resistive RAM was storing multiple bits per cell. And then with appropriate weight encoding for neural nets, we could actually improve the accuracy of inference by 2.3x, because on the same hardware, we can now store a bigger neural net. So this is an example of a cross-layer optimization between technologies, which is resistive RAM, which is circuit techniques, which is how you program those resistive RAM cells, and also using architecture and system level techniques, all the way to the application where we have optimized neural net encoding that actually gives us 2.3x improved inference accuracy when we can store bigger neural nets thanks to this multiple bits per cell. Remember that when you think of multiple bits per cell resistive RAM arrays, new RRAM algorithms, especially for writing into the resistive RAM, is key. So as shown over here, so you can see that we have 8 regions, and you can see that the widths of these regions, which is like the resistance that's storing actually, that's acting as the memory, that has been allocated unevenly, and that is extremely important. How do you make this multiple bits per cell work for resistive RAM arrays? If you use flash techniques, which also can store multiple bits per cell, that does not work for resistive RAM. These new algorithms that enable correct reads and writes in spite of resistive RAM variations. And I'm truly excited to talk about this really new paper that just got accepted just recently. It is already on IEEE Explore, and it will be published in the March issue of the IEEE EDL, where we can increase in density of this resistive RAM by leaps and bounds by having 1T 8R resistive RAM arrays. So in general, people have 1T 1R resistive RAM arrays, which would mean you have one transistor that's controlling one resistive RAM. Now, if you do that, the resistive RAM is on top of the transistor, and the transistor footprint is much bigger than the resistive RAM cell. So your density is dominated by the transistor footprint. And the question is, how can you pack more resistive RAM cells on the same transistor footprint? And that gives rise to this idea of 1T 8R resistive RAM. And in each of these resistive RAM cells, in this 1T 8R structure, we can store 4 bits per cell, which is 16 levels. So this is a record to have 4 bits per cell times 1T 8R resistive RAM arrays. I strongly encourage you to read this paper. This is in collaboration with Skywater Technology Foundry. So we looked at carbon nanotube transistors, we looked at resistive RAM. Now let's look at three-dimensional integration. The way three-dimensional integration works today is what I call sparse 3D using these big fat pillars, or TSVs, or through silicon vias. I liken TSVs to the 3 bridges that connect San Francisco with Berkeley. And as a result, every time you travel between these 2 busy cities, San Francisco and Berkeley, you are always stuck in traffic. That's exactly what's going on with our computing systems. We have the compute chip, which is a very busy city thanks to Moore's law. We have the memory chip, another busy city thanks to Moore's law, but we are just connected by these big fat pillars, the TSVs, that are the 3 bridges between San Francisco and Berkeley. Instead, if we can build millions of bridges between San Francisco and Berkeley, we will never be stuck in traffic. How would you build very strong vertical connectivity, very dense vertical connectivity between compute and memory? The densest vertical connectivity well known to humankind is perhaps the vertical vias, the interconnect vias, the back end of line vias that we already use in our integrated circuit chips today for metal interconnects. So then the question is, can we put transistors and memories on the upper layers of our integrated circuits to create what would be called a dense monolithic three-dimensional integration? Now, using conventional silicon technologies, it's very difficult to implement monolithic three-dimensional integration, because to create a silicon transistor would require 1,000 degrees C in a commercial foundry today. And when you actually build such a silicon transistor on the upper layer of an integrated circuit, everything else that you built underneath would be very severely damaged. But the component technologies that I just talked about today, for example, carbon nanotube FETs and resistive RAM, they can be naturally built at less than 400 degrees C. So now, what you see is that in addition to their device level benefits, the device level benefits of carbon nanotube transistors or the device level benefits of resistive RAM, you enable a new architecture using this ultra dense monolithic 3D that is not possible with existing silicon technologies. Remember when I was talking about nanosystems, I said that it's absolutely crucial to build new architectures, to enable new architectures that are extremely difficult with conventional technologies. This is an example of that. Now, the question is, can you actually build such a monolithic 3D integrated chip? And the answer is yes, we did that. In 2017, in Nature, we demonstrated this first three-dimensional nanosystem using 2 million carbon nanotube FETs and a megabit of resistive RAM, in a monolithic 3D stack. For the using the carbon nanotubes, we implemented like a machine learning accelerator. For this, example, we implemented support vector machines. I already talked about a megabit of resistive RAM. For abundant data computing to grab massive amounts of data from the external world, we implemented millions of sensors using carbon nanotubes on the uppermost layer. Remember, I always emphasize the importance of ultra-dense vertical connectivity. And you can see over here, there is no through-silicon vias or TSVs. We just use the conventional dense back-end of line vias. And this structure, this 3D nanosystem that we built, that could grab data from the external world at terabytes per second, store the data on chip using the resistive RAM, and perform computation in situ for extensive and accurate classification. Now, this is a dream of a so-called IoT, and this shows that we can actually demonstrate actual working three-dimensional nanosystems in actual fabrication facilities, and this is an example of that. We also implemented, this was at ISSCC 2018, we demonstrated hyperdimensional computing. This is in collaboration with our colleagues at UC Berkeley, which is a brain-inspired computing model, which is beyond today's conventional neural nets. And for this hyperdimensional computing demonstration, we exploited the inherent variations of resistive RAM and carbon nanotubes in positive ways. We exploited the resistive RAM gradual reset that you can naturally do with resistive RAM without having to implement big accumulators. And we exploited the application resilience of this AI workloads. And at ISSCC, we actually live demonstrated language classification and one-shot learning, in real life. So I could end this presentation at this point, and I could tell you, well, I talked about the technologies. I showed you actual hardware demonstrations, my way or highway. But I know better. I know that many of you have many other great ideas, either at the device technology level, maybe new integration technologies, or maybe even new architectures. So that's why we built a new simulation framework, the NEXT simulation framework. This was done, headed by my former postdoc, Mohammed Sabri Ali. He's now a professor at NTU in Singapore. So this simulation framework, on one end of the spectrum, it brings in heterogeneous nanotechnologies for logic, for memory, for integration. And on the other end of the spectrum, it looks at abundant data applications, for example, using frameworks such as PyTorch or TensorFlow and others. And then it performs system-level analysis, explores architectures, and does a real physical design to make sure that those architectures are actually viable, and then computes and estimates energy and execution time and thermal behaviors and so on and so forth. Using this NEXT simulation framework, we looked at a wide spectrum of applications: deep learning, graph analytics, conventional machine learning, and so on and so forth. And as you can see, that across this wide spectrum of applications, you see massive benefits at the tune of 1000x improvement in energy and execution time. Remember, that's our metric for computing performance. And very importantly, using existing software. So this NEXT simulation framework, we have been using that for many cases, for various situations, various scenarios. To quantify the benefits, the massive benefits that this NEXT approach brings. So as I told you, at a scale of 1000x. And also to co-explore the interactions, the interplay between technology, architecture, and applications. For example, why would you need very dense vertical connectivity? What would happen if you just were stuck with, for example, existing through silicon vias, and you take a memory chip and a compute chip, you have a few through-silicon vias at a very high pitch between them, and you use those very few through-silicon vias to connect a memory chip and a compute chip. How much benefit would you get? You can see that there is a very significant benefit by going to this ultra-dense vertical 3D connectivity where you immerse computing and memory, especially with our next approach of monolithic 3D. You get up to a scale of 1000x benefits. And I'm very proud to also highlight that these are not just some hardware demonstrations that we did in our lab. So, I showed you the 3D nanosystem, I showed you the hyperdimensional computing hardware demonstration. Our MIT colleagues, Professor Max Schulaker's group, they demonstrated a 3D imager, for example, at VLSI Symposium in 2019. But beyond these lab demonstrations, all these technologies, the carbon nanotube FETs, the resistive RAM, the monolithic 3D, they're actually working in a commercial silicon foundry. So this proverbial lab to fab is already happening as we speak. This is a collaborative project as part of the DARPA 3D SoC program between MIT, Stanford, and Skywater. And I'm very proud this was announced that these technologies, all these three technologies together, are working in a commercial silicon foundry. So these things are absolutely practical technologies that are completely compatible with commercial silicon technologies. And with this lab to fab transition, that creates many nanosystems opportunities. For example, now you can actually build interesting nanosystems through a cross-layered exploration and optimization between devices, circuits, and architectures. For example, you could actually think about very dense compute on the upper layers of the 3D stack, and then you have to think about how to deal with thermal. I briefly mentioned that earlier in this presentation. And you can think about new architecture and software optimizations. Obviously, I have a few minutes left, so I won't have the time to go through each of these. Instead, I will focus on one example of a cross-layer approach between device, circuit, and architecture that is enabled using these technologies that I'm talking about. So to motivate this cross-layer approach, let us look at what we have been talking about until now. We talked about the walls, the memory wall, the power wall, the miniaturization wall, and then I introduced the next concept to overcome all these walls simultaneously. And I showed you that this can be built in real life, in actual hardware. And I also showed you that the benefits of this next approach are humongous. And why so? That's because this next approach allows us to build what I call is a dream chip. We have all compute and all memory on the same chip, accessible very quickly at a very low energy. So this is a dream chip all of us have. Now, what really happens is that once we build this dream chip, the world can make use of this dream chip, and the applications will become bigger and bigger, which means that this dream chip will continue to be a moving target. And in some sense, this dream chip will always be infeasible, because once you have built a dream chip, your application has gotten bigger, which means you have to build a bigger dream chip. Since we cannot build a dream chip today, right, and that's the whole purpose of introducing Next, we rely on off-chip memory accesses, and I already talked about the memory wall being a major challenge. So for example, let's say that this dream chip that I was showing on the previous slide, you want an amount of memory which is n times m. But let's say that on today's compute chip, you can actually just integrate an amount of memory which is m. So as a result, what you do is that instead you put an off-chip memory which is the amount of n minus 1 times m. So the overall memory in the system is n times m, but you have the memory wall. And as I was saying earlier, to overcome this memory wall, and in addition, the power wall and the miniaturization wall, you use our next concept. The question is, can we do better? Since this dream chip is going to be a moving target, and this memory world is humongous, can in Nature Electronics. This is a collaborative project between Stanford, CELAT, and NTU Singapore, and Facebook. The idea is that once our next chips enable enough on-chip memory, and remember this resistive RAM that we were talking about, which allows quick on-off. I can turn a chip on and off very quickly. So I can take n of these chips, n of these compute chips with enough on-chip memory, and then I can put them on a network. And if I have enough on-chip memory, if I can turn the chips on and off very quickly, and if I use very special mapping of my application that use the inter-chip network very sparsely, then I can create an illusion of my dream chip, although I have not built my dream chip. And when I say illusion, I mean that the energy of this overall system will be within a few percentage points of my dream chip, and the execution time of my overall system will be within a few percentage points of my dream chip. Now the question is this something possible? And in that Nature Electronics paper, we have shown that this is actually possible. And I will go through in the next few slides that how a combination of this cross-layer thinking between technologies, architectures, and applications allow us to do so. Now, illusion is different from traditional multi-chip parallelization. It actually is a superset of traditional multi-chip parallelization because illusion actually enables you to create interesting schedules by taking advantage of this enough on-chip memory, quick chip on-off, which is otherwise not possible. So to build this illusion system, so here is this, like a little picture of this illusion system, which I'll get into more details of. Individual chip in this illusion system we built in collaboration with CELAT, and that contains resistive RAM with industrial silicon CMOS. You can see the industrial silicon CMOS is at the bottom layer, and you have CELAT's resistive RAM on the upper layers. With this chip, we were able to do two things. In the active mode, so far as the compute part of the chip is concerned, we actually were able to do an apples-to-apples comparison with industry chip with on-chip flash. And we were able to demonstrate that with this on-chip RRAM, we achieve 10x lower energy versus on-chip flash. So, this resistive RAM technology allows us to have enough memory on chip, which is very efficient and dense. And very importantly, we can very quickly turn this chip on and off. So here is a little scheduler, as you can see, on this chip. And in the shutdown mode, this little scheduler is on, which turns the chip on and off. And we were able to show in actual hardware that we could turn this chip off 5,000x quicker compared to a flash chip. So remember, when we were talking about the illusion system, we want to have enough dense and efficient memory on chip, number one. That is enabled the RRAM I showed on the previous slide. And it's extremely important that we are able to turn things on and off very quickly, again, which is enabled by the RRAM. We can turn things off, for example, 5,000x quicker compared to the flash chip. And with that, with new illusion mappings, so we took AI workloads, AI inference for the Nature Electronics paper, and we had clever mappings that you would not typically use for conventional multi-chip parallelization. And I encourage you to read the Nature Electronics paper that has the details. In hardware, using an 8-chip illusion system, as shown over here, we were able to demonstrate that we achieve an illusion dream chip, which means not only do we achieve the same functionality, because remember, using 8 chips, we have 8x more memory in the system, which means we have achieved a dream chip, which is 8x bigger. Not only that, we can achieve the energy of the illusion system is only 4% more than the energy of a dream chip that you could not otherwise build. And the execution time of the illusion system is only 3% more than the execution time of a dream chip that you could not otherwise build. And this is measured data for AI inference. So if you think of EDP or energy delay product, or our performance metric with energy times execution time, you are within 7% of a dream chip in spite of implementing an illusion system. And that is enabled by, again, I repeat, enough on-chip memory, which is enabled by this dense and efficient resistive RAM on each of these individual chips, quick chip on and off, which is also enabled by this resistive RAM, and clever new mappings, which are the illusion mappings. I strongly encourage you to read the paper. A clear example of a cross-layer exploration and optimization between device technologies, architectures, and applications. From a reliability standpoint, if you think about resistive RAM or any non-volatile memory technologies or any non-volatile memory technologies, depending on which one you are using, you have to worry about endurance. If you write too many times into the non-volatile memory, the non-volatile memory might fail with respect to writes. So for our illusion system, we were able to come up with a new approach, which is called distributed endurer. And this is measured data on this slide. You can see that if you did not have any resilience, after 1 year of operation, you have significant degradation in inference accuracy, for example. This is measured data. But with distributed endurer, on the full illusion system, we could measure 10-year worth of lifetime. Now, you could ask me a question that how could we measure this for 10 years? We didn't have these chips for 10 years. I'll be happy to answer. We were able to measure 10-year lifetime using this distributed endurer for this AI application on this illusion system. And this creates a great opportunity that I would like to focus on in the last part of my presentation. So for the past 60 years, this photo credit goes to Professor Philip Wang, my colleague. We have been through this miniaturization tunnel. The only way to improve technologies was to make things smaller and smaller and smaller, the so-called Moore's law, the so-called two-dimensional miniaturization. Moving forward, we can go beyond this miniaturization tunnel that we followed for the past 60 years. And I'm truly excited about this possibility, and that's what I'm going to focus on in the last part of this presentation. And this is what I call illusion scaling beyond the conventional two-dimensional scaling. We already talked about the next dense 3D chips, right? That was the focus of this presentation. And I showed you that this next technology, this next concept is actually working in commercial silicon foundries using a combination of carbon nanotube FETs, resistive RAM, and dense 3D. And now what we have to think about, what illusion enables, is that you take this next dense 3D chips and you take many of those and put them together, perhaps on an interposer. And now we have to think about how we implement a very efficient interchip network that would connect this next dense 3D chips. And because of illusion, that would create a new way of scaling our systems. So let's look at that on this slide. So as I was talking about before, for the past 60 years, we have been following the y-axis of this slide, which is more and more on-chip integration. Today, we use on-chip integration. We achieve on-chip integration using two-dimensional miniaturization. Moving forward, we are going to use dense 3D. So we have more and more capacity, for example, per chip, if we are thinking of on-chip memory, for example. That's the y-axis. The x-axis shows interchip network performance, which is, I used a metric which is gigabytes per second times bytes per picojoule. Obviously, higher values of this metric normalized to, for example, PCIe, would be better, as shown on the y-axis. And how do you achieve better interchip network? How do you achieve a better interchip network performance? That's through better interchip integration. So now we are thinking about, instead of a tunnel that we followed for the past 60 years, I said, now we have a football field. We have a full two-dimensional space to play on. On-chip integration knob and interchip integration knob. Now we cannot use this on-chip integration knob and the inter-chip integration knob blindly. We have to orchestrate them. We have to use them in tandem. So what's shown on this slide is these red lines that you are seeing over here. These are ISO illusion EDP lines. For example, on this line, the illusion EDP is within 10% of the EDP, or the energy delay product, of the dream chip. Here, the illusion EDP is 2 times the dream chip. Now remember, the dream chip is something that we cannot achieve today. And as a result, we have to rely on off-chip memory, and as a result, we have the memory wall. So as a result, what we can achieve today is way, way, way away from a dream chip. So achieving within 2x or 10% or even 1% of the dream chip, so far as the energy delay product is concerned, is what the world wants. This is the massive benefits that I was talking about using our next approach. What is interesting is, if you look at one of these ISO lines, you see that the technologies are fungible. That means you could actually achieve this illusion EDP using a lot of integration when your inter-chip network is not great, or by having a really high-performance inter-chip network, and as a result, you do not need a lot of on-chip integration. So on-chip integration and inter-chip integration, these are fungible. And really, it depends on how we orchestrate these technologies so that we actually achieve practical technologies, optimized technologies, and we are on one of these illusion EDP lines. That's the first point I want to make. And the second point I want to make, which is equally important, is moving forward to scale performance, what we need is, we want to go over here along this diagonal, right? That's the preferred point. That's how you get more and more performance. Which would mean that to go from one of these lines to a better line, for example, this is where the illusion EDP is 2x the dream EDP, and here the illusion EDP is 10% the dream EDP, or the illusion EDP is 1% of the dream EDP. To go from this line to this line, or from this line to this line, there are multiple ways to do that again, right? You could keep the inter-chip network performance the same. As a result, you would need a lot of integration on chip. Or you could keep the integration of the chip the same, in which case you will need a lot of improvement in inter-chip network performance. But if you actually go diagonally from one line to another line, you need only a little improvement in on-chip integration and some improvement in inter-chip network performance. And the combination of the two will get you to this point very quickly. So moving forward, this creates a new concept of scaling, which I call new illusion scaling, where you orchestrate on-chip integration with better inter-chip integration, and you achieve massive benefits. So this brings me to the end of my presentation, and I want to make 3 really important points. Next, nanosystems are achievable today. That's my first point. In a commercial foundry, I demonstrated that our technologies, NanoFETs, the resistive RAM, and monolithic 3D are working as we speak. Which means that I started with this national academic study asking the question, the future of computing performance, game over or next level? My tongue-in-cheek answer is, it's game on to the next era, the next concept that I talked about in this presentation. And thanks to NEXT, I believe that enables this notion of what I call this new illusion scaling, which brings massive benefits for a wide range of applications. So thank you very much for your attention, and I'm happy to take questions. Ricardo, you're perhaps speaking. I cannot hear you.
Sorry, it was unmuted. So thank you very much for your very nice, interesting, and inspiring talk. So we have here some questions. First one from Pedro Toledo, that is now in Italy. So he's saying, very excellent and exciting presentation. What about the analog part for sensing the world? What are the future perspectives to integrate with all the fancy 3D systems shown here?
Thank you very much for Pedro for asking that question. Obviously, as you can guess, that the scope of this project is tremendous, and I wouldn't have been able to do this work without a lot of collaborators. So I'm really thankful that you asked the question about about analog circuits. Actually, guess what? The first kind of medium scale demonstration of a system that we presented at ISSCC in 2013. This is in collaboration with Professor George Gillen, who many of you know from KU Leuven, was actually an analog system, an analog converter. And so yes, you're absolutely correct. There are tremendous opportunities when you think of sensors. You think of interface circuits with the sensors and then coming to the computing. And especially in the 3D stack, that creates tremendous opportunities, for example, using these new technologies. So the answer is yes. I'm not an analog circuit designer, but I'm truly thankful to George because in collaboration with him, we are able to demonstrate that. And as you know, also with analog circuits, they're also becoming very digitally inspired. And that's where some of these new technologies become very handy. Despite their variations and all that, you can build interesting analog circuits and systems. I would strongly encourage you to look at some of George Gillen's work in that space.
Thank you. We have another question by Professor Claudio Diniz. Thank you for the excellent talk, Professor Mitra. Could you comment about the challenges on designing and integrating EDA tools to deal with the design of those chips?
Thank you very much. You brought up a very important point, which is the EDA point, right? And I did not have time again to get into details, but let me spend a little time talking about it. So I will talk about two things. So remember, in the context of this, the next simulation framework, I very briefly touched upon this, that when we started doing this work, there was very little support, even in academic research, where we could actually pick an EDA tool and actually do a full place and route of a 3D chip. So Tony Wu, my former PhD student, he's at Facebook right now, he actually built an EDA framework actually to do that, and he was hacking around commercial EDA tools to do this. But I would like to highlight this work that's going on in our DARPA 3D SoC program, and this part of the work is led by Professor Sankyu Lim from Georgia Tech. And his team is actually building a physical design infrastructure, for example, for this monolithic 3D integration using our 3D SoCs, using carbon nanotubes, resistive RAM, and so on. So I would strongly encourage you to look at his work. But that's not the only aspect of EDA. I would like to highlight another aspect of EDA, which is equally important, which is, I talked about illusion, right? When you have illusion, you take a big AI workload and you map it into these multiple chips and you create this illusion of this dream chip and so on and so forth. I actually think that moving forward, today when we think of high-level synthesis aspect of EDA, for example, right, we still think of a single chip. Now moving forward with this concept of illusion, I think that opens up the space of the high-level synthesis aspect of EDA to multiple chips. So how do you create an system, illusion system through high-level synthesis? I think that would be an exciting new topic. I haven't seen a lot of work in that space. That's the second thing. The third aspect of EDA, and I'll stop over here because there are lots of questions coming in, which I'm very thankful for. The third aspect of EDA is how do we actually create an infrastructure so that very quickly we can actually explore the vast space? Because now you're talking about a vast space in technologies. Everything has opened up. I tell my PhD students, I wish that I was doing a PhD now rather than doing a PhD 20 years back, because that's when the world exactly knew what to do. So with this vast range of technologies, vast new architecture, domain-specific architectures, and new applications, how do we explore this space? And I think these are tremendous problems for EDA moving forward. I think I got carried away. I'm truly excited about it, but I'll take the next question.
Yes, we have a, thank you. We have a second question by Professor Claudio Diniz. So maybe you could also comment which EDA tools were used to design the chip that you have fabricated?
So so we have used both. So we have used Synopsys and Cadence. And it's not just for the fabrication part. When we actually go and and again, I didn't get a chance to talk about this at all. So for example, when for our analysis, for example, that we do with in collaboration with IMEC, for example, for the carbon nanotube FETs, you can guess that we had to mark around some of the CDA tools. But what we were able to, and this is the beauty of some of our imperfection immune approach, for example, which I briefly touched upon. So most of the techniques are at the internal cell level, intra-cell level. So once you actually have the new library cells for the carbon nanotube technology, for example, you can pretty much press a button on a Synopsys design compiler to create your circuits. But having said that, I would strongly encourage you to read a paper called Dream. This was done by two of my former students, Professor Max Schulacker and now a professor at Harvard University, Professor Gage Hills. So what they were able to do is they could actually change the logic synthesis a little bit. Like should NAND gates follow NAND gates, should NOR gates follow NAND gates, and so on and so forth. And by doing that, they could show that you can actually even make these carbon nanotube circuits even more immune to metallic carbon nanotubes, for example. So please, take a look into that. Again, I agree the scope of the question because I think this is where some of the exciting possibilities moving forward.
Thank you, Mitra. So now a question by Professor André Luiz Aita from Federal University of Santa Maria at Rio Grande do Sul, Brazil. So great talk. Thanks for providing us with so many exciting concepts and ideas. Wondering about alignment of those vias over layers.
Yeah, thank you. So, you hit a very interesting topic. And again, this is going to take me a little time to, to talk about. So, for example, there are many ways of doing integration in 3D. So here we are using monolithic 3D. And the reason we are doing that is because just think of how an integrated circuit is built today, right? So you have transistors in the bottommost layer, and you create a bunch of vias, and you create the first layer of metal, create a bunch of vias, create a second layer of metal, bunch of vias, third layer of metal, and so on, right? And a very important aspect of that is you do not have to worry about alignment. So it's all dealt with by lithography, right? Now you could think about alternative ways of doing integration, where you could say that, I integrated this part of my chip, on this wafer, and that part of my chip on that wafer, and then I brought, them on top of each other, for example. And that's where you have to worry about the alignment of the vias, basically, right? The alignment of the contacts. Now, people have been trying very hard to do this. For two wafers, for example, or one chip and one wafer, they use bonding techniques. The question is, how can you actually go and create multiple layers and not worry about alignment? And if you have to worry about alignment, then what happens is these vias become very sparse and you do not have the dense connectivity. So if you're interested in that kind of research, again, this is actually the perfect golden opportunity to do that kind of research.
Thank you. So now a question by Rogério Paludo from Federal University of Santa Catarina, Brazil. Are the 8 chips active at the same time? What are the limitations by the hosts?
Thank you. Thank you very much. This is for the Illusion system. So the 8 chips do not have to be active at the same time, right? It all depends on your workload. Now, if your workload is such that it's embarrassingly parallel and there is no communication between the 8 chips, of course, the 8 chips can be active at all times. But here, what we are doing is that we are mapping a bigger workload into these 8 chips. So obviously, as you can guess, that there will be bubbles, right? Because we want to minimize the messages and still achieve the dream. So when there is a bubble, that means one of the chips may be inactive for a certain period of time. So when it is inactive for that period of time, you do not want to go and incur leakage power. You do not want to waste energy just waiting. And this is why this very quick turn on and turn off is absolutely crucial to make this illusion work. And I hope that answers your question, but spot on question.
Okay, thank you. So now a question by Professor Altamiro Suzin, Federal University of Rio Grande do Sul at Porto Alegre, Brazil. So thank you very much, excellent. I wonder if we could try high-level systems specification in order to optimize resource usage, to rely on essential data and just sufficient operand precision.
Fully agree. Fully agree. This is what I was referring to, and so I'm sorry, I'm going to philosophize a little bit over here. Okay, I'll take a minute to do that. So I had a wonderful stay at EPFL in Switzerland, hosted by Professor Nani Di Micheli and Professor David Atienza. This was in 2014, and when I was doing that, I had the honor to co-author a paper with Professor Di Micheli on in the proceedings of the IEEE, and this is talking about logic synthesis or synthesis in general, EDA in general, as a nanotechnology enabler. This is and I want to emphasize this point, right? That it's not that there is a technology and then we create some EDA. We do that and that will happen, okay? And that's what the EDA companies will do, right? They always ask you that, is the foundry implementing something? Okay, here is my EDA support. But the question that professor just asked, it's extremely important that EDA can be an enabler for these new technologies. Because we have these new technologies, as a result, we have to think of new EDA. And and that is, I mentioned physical design, like the work by Professor Sankyu Lim. Like a few years back, I remember David Pan, Professor Di Micheli, and C.E. Letty, they actually did an interesting work on a CoolCube, for example. And as you know, as I showed in this presentation, Letty is also a deep collaborator with us. So that's in the physical design level. Similarly, in the logic synthesis level, there is interesting work coming from EPFL, for example, where they're looking at majority logic, for example, for new kinds of technologies. But now, once you have these new architectures and now the illusion systems, I'm completely agreeing with you that now we have to think about high-level synthesis. And how do you do high-level mapping and how that automatically happens thanks to these technologies. And as a result, you can actually enable these new technologies by bringing their capabilities that may not be there in existing technologies. So thank you. I hope that answers your question.
Thank you. So we have now a question by Cesar Diaz, Federal University of Rio Grande do Sul. Thank you for sharing your exciting research, Professor Mitra. Could you talk about exploring in-memory computing applications from this approach?
These are all great questions. I think we are going to, Ricardo, have to come over to Brazil, it seems like, sometime, And yeah. I absolutely love Iguazu.
You are invited.
Thank you.
Always invited.
Thank you. So yes, again, that's another topic. I think that could be a topic of another 1-hour presentation. But let me tell you very briefly. So as you can see, that the whole reason that we are doing this, resistive RAM, is because of inside memory computing, for example, right? So you could implement inside memory computing using the resistive RAM. But at the same time, you have to think of the following. So yes, inside a resistive RAM array, you implemented an inside memory computing. Now, if you have a big AI workload, it's not that you're going to have one large array to implement the inside memory computing in one large array, right? You will have multiple small arrays. And now you might have to think about this illusion system inside a chip, where each sub-array is implementing some inside memory computing, and you're doing an illusion between these sub-arrays, for example, to create the benefits of a big inside memory computing that you couldn't do because the memory has to be implemented in sub-arrays. So those kinds of concepts will be very important moving forward. There has to be an apples-to-apples comparison between just inside memory computing versus just illusion versus kind of probably a combination of this inside memory computing and an illusion system.
So thank you. So we have now a question by Professor Ibrahim Elfadel from Khalifa University in Abu Dhabi, United Arab Emirates. So great talk, Subhashi, as usual. What is your perspective on foundry landscape of the next technology? Who will be able to take illusion integration to the ultimate limit?
I have lost track of the question. I was trying to read the questions, but thank you very much for all the great responses that are pouring out. So I highly appreciate. So it's okay for me to lose track of these questions coming in, but this is fantastic. Thank you. So hi Eb, how you doing? My answer is that so when we started this next project, right? First, everybody asked the question, can you actually build it? Then, we built it in our Stanford fabrication facilities, right? And then, people ask the question, oh, good, you did it in your Stanford lab. Can it actually work in a fab? And I'm actually so thankful to DARPA, and the DARPA 3D SoC program. They came in at that point in time and they literally told us that, look, if you propose a project that you're going to just continue doing this thing in your Stanford lab, we are not going to fund you. We are not interested in that. The only thing we are interested in is, can you show this in an actual foundry, right? So right now, at the Skywater Technology Foundry, these things are working. And that's actually is a perfect place for doing this kind of work. First of all, this is very risky technology because this is new, right? For a fab to take 3 new ideas at the same time, right? Carbon nanotube transistors, resistive RAM, monolithic 3D. It's crazy, right? And they did that, and they're making these things work in real life, which is fantastic. And I'm sure that now that these demonstrations are happening, that creates more confidence in people's minds that, hey, these things are feasible. They actually work in an actual silicon foundry. This is not like some, like a boutique foundry doing something very special. So I'm absolutely confident that moving forward, more and more people will step forward. I actually even know that in many places, people are actually thinking about these things. Remember, the key important point I want to highlight is, next is a concept. Next is not a solution. Next is a concept. And I showed you one implementation of next using carbon nanotube FETs, resistive RAM, monolithic 3D, and so on. There could be many other implementations of next. But I'm absolutely confident that moving forward, the world will need next concept. And many foundries will actually embrace this idea. This actually goes back to, so Ricardo, thank you for inviting great speakers, for your CASS presentations. So, I saw, in the fall you had, Professor Ian Rabai, a good friend of mine, Professor Alberto Sangiovanni Vincentelli, Nani gave a great talk, Professor Maciek Ogorzalek from Poland. When Maciek was talking about 3D in his presentation, he was actually talking about various ranges of 3D. So again, you do not have to just think about my specific way of implementation. That's just one implementation. Next is a concept, and we have to be very innovative and creative about how we can realize the next concept, and in conjunction with illusion, for example, in various different ways, and that's where I think the excitement is going to be moving forward. Now, Abe, if I knew the real answer to your question that foundry so and so would be doing this, then I would be filthy rich by now.
So thank you very much, Abe Mitra. So I have a last question. In your vision, when you think we are going to have a commercial microprocessor system on chip using 3D technologies?
Well, first I will give a tongue-in-cheek answer, but I actually know the spirit of your question. So the spirit of your question is not answered by my tongue-in-cheek answer. My tongue-in-cheek answer is, we are already having, processors with 3D technologies, but those are, TSV kind of, for example, packaging, right? But clearly you're not asking that question. I fully understand that. So again, I do not know the specific answer to your question that, when, it would happen. As I, answered to Abe, if I knew the answer, I would be filthy rich by now. But having said that, one thing I can tell you that this will happen. And the reason I'm saying this is because, I already mentioned the commercial, foundry, right? The Skywater Technology Foundry. But obviously, I'm aware of other activities that are going on in the, in the industry that I cannot really talk about right now because I'm not allowed to. But let me tell you that there is deep interest in these things from multiple players, actually, and they're coming from a completely different angle. Some are interested in very high-end technologies, right? Bleeding edge. Some may not be pushing lithography that much, but they might be interested in other classes of applications, and they're interested in this technology. So far as these technologies are concerned, so far as these concepts are concerned, I can assure you that that's going to happen. I do not want to go on record giving you a date.
Okay, thank you very much. Very nice answer. So thank you very much, Professor Mitra. So before closing the session, I would like to remind you of next talks. So next week we are going to have the talk by Professor Helen Lee from Duke University, talking about efficient deep learning at scale. Then we have already here the flyer for the talk by Rajesh Gupta from UC San Diego, talking about programming human space. So we have already also confirmed several other talks for this year. I'm not going to show the other flyers now, but I hope to have your participation also in the next ones. Also, if you missed some of the talks last year, they are all recorded and available at this YouTube channel of CASS Rio Grande do Sul. Also, if you want to regularly receive more information about the talks, please subscribe to this YouTube channel if you have not done yet. We have also in the YouTube channel a set of 20 industrial talks that were done last year, trying to do some coverage of companies that are working on microelectronics in Latin America. And if you go there, you are going to be surprised with several points. I can just tell you that there is one company in Brazil, NXP, that when it was free scale at that time, they designed a chip that is being used as part of the motor control in all Formula One cars nowadays. So this is an interesting point. We have also some companies in Latin America doing design using 7 and 5 nanometer technologies. We also have in the YouTube channel a set. You're not seeing all of them here in this flyer, but of the CASS workshop that was done in October. So you can, several of the speakers that you can see in this window. And also we have also there the talks related to the digital processing of digital signal and applications school that was done last year. There is also another playlist with some of the international talks at the microelectronics school. And so again, we have in a few weeks the LASCAS 2021. So free registration to CASS members. And then in Micro 2021 and the South Symposium Microelectronics will be in the last week of April. So fully virtual this year. So I hope that 2022, it will be able to be face-to-face again. So as you know, each year in a new location in the region. And then here, the last week of July, so the CASS Seasonal School on Monolithic 3D. So it will be an international school. I hope to have a talk of Professor Mitra in the school. So he is already being invited. Also, the fourth edition of the CASS School on Physical Design Automation. That, as you know, the first one was in Porto Alegre, then second one was in Chiayi, in Taiwan, the third one in Beijing, China, and now the fourth edition in Florianópolis, Brazil. And then Ceresa, the School for Circuits Tolerant to Radiation Effects, the 17th edition will be here, I hope, face-to-face, and 2022 edition will be in Switzerland, at CERN. So thank you all for attending this very wonderful talk by Professor Mitra. Thank you again to start our series of 2021 talks at a very high level. So thank you very much. Thank you also to all participants that attended this talk. And I see you all next week, always on Friday, same hour, 1:30 p.m. for the Helen's talk. So bye-bye.
Bye-bye. Thank you very much again for having me. All the best.